Hello students, welcome back to SGC online chemistry classes. This is lecture number 9 on the topic coordination compounds. Well dear students, before we take the next heading, let's recap for a minute of time regarding the part what we had in the last class. Dear students, from the last videos you have come to know regarding the bondings in coordination compounds with the help of valence bond theory. 4 examples we have taken, and later the merits and demerits of valence bond theory we have collected. To overcome those limitations, another theory which we supposed to study as per the syllabus is none other than CFT, nothing but a crystal field theory. Let's start with crystal field theory and what are the points according to this theory, and followed by its application in today's class. So the heading begins with crystal field theory. Crystal field theory. So this theory, crystal field theory, which is an electrostatic model, describing orbital degeneracy in the transition metal complexes due to the electrostatic field produced by the ligands. Due to the electrostatic field or static electric field produced by ligands. I repeat, this CFT, crystal field theory, it is an electrostatic model that describes orbital degeneracy in the transition metal complexes due to the static electric field produced by the ligands. Well, here we have some points to understand this theory. According to CFT, first point, the point assumptions of CFT theory are the bonding between the central metal ion and the ligand is purely ionic in nature. Come on. Bonding between central metal ion and ligand. Central metal ion and ligand is purely ionic, nothing but electrostatic, is purely ionic. So this is the first point of this CFT theory. What CFT theory says? First, the bond that exists between the central metal ion and the ligand is purely ionic bond, ionic in character, nothing but electrostatic in character. First point. Point number 2. Ligands are considered as point charges. Ligands are considered as point charges. Ligands are considered as point charges in case of anions, and dipole in case of neutral ligands, and as dipoles in case of neutral ligands, in case of neutral molecules. So this is the second point. After considering the bonding between central metal ion and the ligand are purely electrostatic, purely ionic in nature, The second point says ligands which are considered as point charges. Ligands are considered a point charges for especially anions and dipoles in the case of neutral molecules. Point number 3, that the interaction I can tell you, the interaction between central metal ion and ligand, the interaction between central metal ion and ligand arises due to the force of attraction, arises due to the force of attraction between positively charged metal ion and negative dipole of the ligand, So this point is very clear. See, when the bonding between the central metal ion and the ligands, when they were said electrostatic, ionic means the bond that exists between the two charges, one with two opposite charges, or two charges with opposite sign. See, third point says, according to CFT, the interaction between the central metal ion and the ligand that arises due to the electrostatic force of attraction between positively charged metal ion and the negative dipole of a ligand. Come on, point number 4. This interaction. So what this fourth point says, this interaction between metal ion and the ligands, what it does, the interaction between the metal ion and ligand, what happens? The degeneracy in the orbitals gets lifted. I repeat this point. Due to this interaction, I repeat very clearly, due to this interaction, what happens? The degeneracy of d orbital is lifted due to this interaction. The degeneracy in d orbitals the degeneracy in d orbitals is lifted to cause splitting of orbitals, very clear. Yes, I do repeat with the fourth point. Retrace once. According to CFT, the bonding between central metal ion and ligand are purely ionic. The ligands are considered as point charges in case of anions and dipoles in case of neutral molecules. The interaction between central metal ion and ligand arises due to the force of attraction between the positively charged metal ion and the negative dipole of the ligand. So due to this interaction, the degeneracy in a d orbital is lifted to cause splitting of d orbitals. So point Fifth one I can add, point number 5. As a result of degeneracy in the d orbital that causes the splitting of d orbitals, the 5d orbitals splits up into two sets due to the approach of ligand. The 5d orbital splits up into two sets due to approach of ligands towards central metal ion. The 5d orbital splits up into two sets due to approach of ligands towards central metal ion into two kinds as T2Z set and EZ set. T2Z set and EZ set. So the fifth point is very clear. The 5d orbital splits up into two sets, one with lower energy, another with higher energy, into two sets, and because of the ligand when they approaches the central metal ion, those two sets are, one is T2Z set, another is EZ set. T2Z is a lower energy set, low energy, possesses the low energy set, and EZ is the high energy, possessing high energy set. So the lower energy set, out of the 5 degenerate orbitals, the T2Z orbitals which are dxy, dyz and dxz, and higher energy EZ orbitals are dx square minus y square and dz square, dx square minus y square and dz square. See, this splitting that further which depends on this splitting into T2Z lower energy orbital or EZ higher energy orbital, this is totally based on the nature of the ligand. That depends on nature of the ligand. A strong ligand gives you high energy set, and the weak ligands that split up to give you lower energy set. This is the approach. These are the ideas given by CFT, the crystal field theory. Further, these points one should remember before we go to application. And this theory, these points, which introduces two important terms, which is crystal field splitting. See, what does it introduces? One is the crystal field splitting. So what is meant by crystal field splitting? One should understand. See, crystal field splitting. These are the terms one should know. First term, crystal field splitting. So what is meant by crystal field splitting? The splitting of degenerate d orbitals, degenerate in the sense the orbitals possessing the same amount of energy. The splitting of degenerate d orbitals into T2Z lower energy set, d orbitals into T2Z lower energy set, and EZ higher energy set due to the approach of due to the approach of ligands, is known as crystal field splitting. One should know what is meant by crystal field splitting. In this, according to this theory, when the ligands they approaches the central metal ion, so what happens? The degenerated d orbitals of the central metal ion, especially a transition metal ion, they split up into two sets. One with lower energy set called T2Z, another with higher energy set called EZ. T2Z, EZ. So that splitting of the 5 degenerated d orbitals into lower energy set T2Z, higher energy set EZ by the influence of ligand is nothing but crystal field splitting. Is called crystal field splitting. Come on, further one should know what is this. One more question might appear. What is meant by crystal field splitting energy? So what is a CFSE? So this is CFS, crystal field splitting. So then what is a crystal field splitting energy? So it is the difference. It is the difference in the energy delta E. The difference between, I do write, the difference between the energy of these two sets is called crystal field splitting energy. Suppose T2Z, the difference between the energy of E of T2Z, E of EZ minus E of T2Z. This difference, the difference between the energy of the EZ set and T2Z set. So the difference between the energy of EZ, this is EZ, let me write. The difference between the energy of EZ set and T2Z set, that is called crystal field splitting energy and is denoted as delta. I hope you followed this. What is meant by crystal field splitting energy? It is the difference between the energy of EZ and T2Z and is denoted by delta. In case of octahedral complexes, denoted as a delta O. In case of tetrahedral complexes, CFSE is denoted as delta T. That's clear. And one more term, which is the indirectly application of this crystal field theory for 1 or 2 mark weightage, one will get what is meant by spectrochemical series. What is the meaning of spectrochemical series? Let me write after this. You may get one more question. Define or what is spectrochemical series? Well, let's look into one more term. What is this term? Spectrochemical series. What is that? Spectrochemical series. Well, so you notice here, this is ligands, negative ligands. We were moving towards neutral. See, I minus, Br minus, SCN minus, Cl minus, and so on. So these nothing but a systematic arrangement of ligands. So you have bromido ligand, chlorido ligand, fluorido, water, aqua ligand, oxalato, so EDTA, ethylene diamine tetraacetato, amine ligand, ethane 1, 2 diamine, so this is carbonyl. So you can see series in the sense systematic arrangement. The arrangement of ligands in the order of increasing field strength. I do write here the arrangement of different ligands, in the order of or increasing order, in the order of increasing in the order of increasing field strength, in the order of increasing field strength, in the order of increasing field strength is nothing but splitting energy. In the order of splitting energy, in the order of increasing field strength or splitting energy is known as what? Is known as spectrochemical series. Is known as spectrochemical series. One more question, do understand the meaning. So as you can see, the systematic arrangement of the ligands, the arrangement of ligands, what is this? The arrangement of ligands, the arrangement of different ligands in the increasing order of field strength, in the increasing order of field strength, that is called as spectrochemical series. Spectrochemical series. Here you have weak ligands. So as based on this end moving with weak, and that end left end weak, right end strong ligands. Weak ligands up to NCS, from I minus till NCS, all these sets are considered as weak ligands. All these sets are considered as weak ligands. These up to here, these are considered as weak ligands. Strong ligands, EDTA onwards, these are considered as strong ligands. EDTA 4 minus onwards, these are considered as strong ligands. So in the spectrochemical series, if one asks name the weakest ligand and the strongest ligand, then remember I minus. So I minus is the weakest ligand, and CO carbonyl is the strongest ligand. Do remember the point of note, stronger the ligand. As a point of note, one should remember as a note, stronger the ligand, higher will be the splitting energy. Stronger the ligand, higher the splitting energy. It means weaker the ligand, lesser is the splitting energy. So these are the terms which are intern application of the CFT. We come across, after collecting the postulate, we come across three terms. One is a crystal field splitting. What is meant by crystal field splitting? The splitting of 5 degenerate d orbitals into two sets, T2Z lower energy set, EZ higher energy set, due to the approach of ligand is called crystal field splitting. Then what is crystal field splitting energy? It is the difference between the energy of the higher energy set and the lower energy set. The difference between the T2Z set and EZ set and T2Z set, what is called crystal field splitting energy. Coming to the heading, spectrochemical series. So what is this spectrochemical series? It is the arrangement of ligands in the increasing order of their field strength. It is the arrangement of ligands in the increasing order of splitting energy, that is called spectrochemical series. In this series, I minus is the weakest ligand and CO is the strongest ligand. So stronger the ligand, higher will be the magnitude of splitting energy. Come on, we'll go to collect the applications of this CFT. So after collecting the terms, such as a crystal field splitting energy, spectrochemical series. Let go with the application question which has appeared. Explain the splitting of, explain crystal field splitting, explain the crystal field splitting in octahedral complexes with energy level diagram. See, explain crystal field splitting. Question is of this kind. Crystal field splitting in octahedral complexes. In octahedral complexes using energy level diagram. Using energy level diagram. This has weightage of minimum 2 and maximum 3 marks. The question: explain the splitting, crystal field splitting, CF in the sense crystal field splitting in the octahedral complexes. We are supposed to study one octahedral, another tetrahedral. So, octahedral complexes using energy level diagram. Well, students, as you know, octahedral complex in the sense you have a central metal atom. So, this is surrounded by octahedral. The central metal ion is surrounded by the 6 ligands. So, those ligands are oriented towards the 6 corners of a octahedron. So, this is what? So, surrounded by ligands. As a octahedral means, one should have an idea. The central metal ion is surrounded by 6 ligands pointing or oriented towards 6 corner of a octahedron. Come on. See, there is a repulsion. There is a repulsion between the electron of the d orbital of metal ion and the electron present in the ligand. See, try to understand. See, the central metal ion which contains a d orbital containing the electron. The electron of the central metal ion and the electron of the ligand, there is a repulsion. There is a greater repulsion between the repulsion between the electron belonging to d orbital of the central metal ion. Do remember, the electron belonging to the d orbital of the central metal ion and the electron belonging to the ligand, there is a repulsion. See, when there is a greater repulsion, try to understand, when the d orbitals of the metal ion, when they were pointed towards the ligand, when the d orbitals of the ligand, when they were pointed towards the ligand, then there will be a greater repulsion. That resulting in the splitting, greater repulsion. Whereas when the d orbitals of the metal were not oriented towards the ligand, that will experiences a minimum repulsion. See, you can notice a greater repulsion and a what you call as a minimum repulsion between the ligand and the d orbitals of the central metal ion. As you know, central metal ion, usually it is going to be a transition metal. Transition metal means d orbitals. As there are 5 degenerated d orbitals, d x square minus y square, dz square, dxy, dyz and dxz. The 5 degenerated d orbitals. The electron present in the d orbital of the metal ion and the electron of the ligand, they repel each other. The repulsion will be more. When these d orbitals, they pointed towards the ligand. If they were not pointed towards the ligand, then what happens? There is a minimum repulsion. See, in the octahedral complexes, if I show with the energy level diagram, see here you have the degenerate 5 d orbitals of the metal ion. These are 1, 2, 3, 4, 5. The 5 lines indicates the 5 degenerate I write degenerate d orbitals of metal ion. The 5 degenerate d orbitals of metal ion. See what happens? What happens when the ligand approaches? There is a repulsion between, they get excited. These 5 sets get excited. See what happens? When the ligand approaches the central metal ion, because of the repulsion between the electron of the d orbital of metal ion and the electron present in the ligand, there is a repulsion. The repulsion will be more when the orbital they point towards the ligand, and the minimum repulsion when they were away from the ligand. Suppose the d orbital, if it orient towards the ligand, that experiences a greater repulsion. If the d orbital, if it points in between, not towards the ligand, then that experiences a minimum repulsion. Here what happens? Out of the 5 degenerate d orbitals, namely dx square minus y square, dz square, dxy, dyz and dxz, the three they point towards intermediate, they point in between the axes, that means x, y, z. See, 3 of them they split to give you 3 sets, I mean a set of 3 orbitals, that is, this will split up into 2 sets. This will split up into 2 sets, such as, see, you have lower energy set. So these are called a T2Z set. See, what are the orbitals involved in the splitting with the T2Z set? Here you have dxy, dz, dxy, dyz and dxz. Why these orbitals? They form a lower energy set because these degenerate d orbitals, dxy, dyz, dxz, these degenerate d orbitals, they were pointing away from the ligands. They were pointing the degenerate, these dxy, dyz, dxz d orbitals of the metal ion, they were not pointing towards the ligand. They were pointing away from the ligand. They were pointing away from the ligand means they experience a minimum repulsion. With the minimum repulsion, their energy is get down and they form a lower energy set called T2Z set. Then, whereas these two other dx square minus y square and dz square, these 2 sets, these 2 orbitals of the metal ion, they point towards the ligands. That means dx square minus y square and dz square, they were pointing along the axes, whereas these three, they were pointing in between the axes. See, when you have x, y and z, so when you have x, y and z, the dx square minus y square, they were pointing along the axis x, y, z. But dxy, dyz, dxz, these 3 are pointing in between the axes, That is the difference. The dx square minus y square and dz square, as they were pointing along the axis, and they point towards the ligand and experiences a greater repulsion. With the greater repulsion, they split into higher energy set, which is EZ easy set. What are those? Those are dx square minus y square and dz square. dz square. See, this intermediate line which is bisecting, here you have the energy difference. See, the crystal field splitting energy in the case of octahedral complex is denoted as delta naught. O stands for what? O stands for octahedral. See, the crystal field splitting energy delta O for the easy set is plus increase by 3 by 5 times of delta naught. Increased by 3 by 5 times of delta naught, and the crystal field splitting energy delta naught for the T2G set is decreased 2 by 5 times of delta naught. So this is the energy level representation for the crystal field splitting in the case of octahedral complexes. Let me clear once. So in the octahedral complexes, since the metal atom is surrounded by 6 ligand, see, there is a repulsion between the electron of the d orbital of metal ion and the electron belonging to ligand. The repulsion will be more when the orbitals were pointing towards the ligand, when the repulsion is less when they were pointing away from the ligand. Out of the 5 degenerate d orbitals of the metal ion, the 3 dxy, dyz, dxz, they were directed in between the axes, whereas the dx square minus y square and dz square, they were pointing along the axis. The one which are pointing along the axis were pointing towards the ligands and will experience a maximum repulsion, because you can see a rise in the energy of those two sets split into easy set called higher energy set. Their energy is get up by 3 by 5 times, nothing but 0.6 times of delta. Coming to the other 3 d orbitals, dxy, dyz and dxz, those, since they were pointing or orienting in between the axes, they were away from the ligand and experiences lesser repulsion. As a result, there will be a decrease in the energy, forming a lower energy set, that is 2 by 5 times of delta naught. So with this, dear students, I conclude today's class, where the crystal field splitting in the octahedral complex is completed. Let's see the crystal field splitting with respect to tetrahedral complex in the next video. Thank you.